All right, so we have this 5-meter long, 200 Newton ladder rests against the wall. The ladder center mass is 3 meters up the ladder. Coefficient of static friction on the ground is 0.5. Piece of aluminum is flashed against the wall, making the force of friction on the wall negligible. The angle between the ladder and ground is 56 degrees. What is the force of static friction exerted by the ground on the ladder? So this is a very intimidating question. It's actually going to take a little bit of time to go through. But we always start with the same thing, is we're going to start with drawing a free body diagram. Okay, we're going to draw the free body diagram. Now, because we're going to be handling some torques in here, because we want, basically it's just sitting there, so the acceleration is 0 and the angular acceleration is 0. So we're going to handle both of those when we're doing a scenario like this. So we need to put the forces where they're acting, because we can't calculate the torques without knowing where the forces are acting. How do we draw a free body diagram? Start with gravity. Gravity acts at the center of mass of an object, right? So that is 200 newtons acting there. That's everything. So now we want to talk about what is touching the object. Well, the wall is touching it. It exerts a normal force perpendicular to the surface here, right? Because that's how normal forces work. Normal means perpendicular, perpendicular outward from the surface here. There's no friction, so there's no force parallel to that surface. Now this one is going to have a normal force from the ground also. So we're going to call this normal force from the wall, and then this is the normal force from the ground. Okay? This side does have friction though. Now it's static friction. Static friction is always the trickiest force to identify, so there's some parallels at outward or inward. Well, because the net acceleration is 0 and the wall is pushing to the left, in order to keep the ladder from moving, this thing has to be to the right. The static friction has to be to the right. Okay? Now, is that everything that is touching the ladder? That is. So we're done with the free body diagram. So now we're going to identify the axis of rotation. So where's the axis? Well, we want the force of the static friction. So we could make either this point down here, this point down here. I tend to make, because the angular acceleration is 0, it's not really rotating, I tend to make the point that is, that would eliminate the most number of unknowns as part of my axis of rotation. You could put center of mass, you could put up here. Either of those would be good, but like, let's just put this one to make the torque calculation easier. Because I always like to minimize my torque. So identify axis of rotation. Now we want to identify the positive and negative direction. So we'll say counterclockwise positive, clockwise is the negative direction. So establish direction. And then now we're going to do net torque equals I alpha. Net torque equals I alpha, which in this case is 0 because this thing is not actually rotating, no angular acceleration. So there's no torques from these guys because the R is 0. But then we're going to talk about this 200 newton. So we're going to draw an R vector from there to there. Okay, so I'll use this lighter color here. There's an R vector from there to there. That's 3 meters, but it's not perpendicular to this. So this is 3. So we need to decompose this R vector into component, because it's not perpendicular to the force. We have to decompose it into horizontal and vertical components. So this would be 3 cosine 56 degrees. And 3 sine 56 degrees. That's the decomposition. And we only want to take the component that's perpendicular to here. So that torque, and then pulling down here would cause the ladder to go clockwise. So that's a negative torque. So that's negative 3 cosine 56 degrees times 200. Okay? Now the other R vector we want to consider, or the other torque, we have to go to the next torque. And let's see, that is, we draw the R vector from here all the way up to this force. Okay, and again, not perpendicular to this force, but, so we're going to decompose it again. And so that letter is 5 meters. So the whole length is 5 meters. So this is 5 cosine 56 degrees. Oops, 56 degrees. And this is 5 sine 56 degrees. Right? So now again, we want to care about the part that's perpendicular to that force there, right? So that's a positive torque because it would cause the ladder to go counterclockwise. So that's plus, this is the component that's perpendicular to here. So that's F and normal force on the wall times 5 sine 56 degrees. And this equals 0. Now notice this only allows us to solve for the normal force from the wall. We're actually asked for the static frictional force. So, but let's solve this anyway. It's going to be 3 cosine 56 times 200, and then divide that by 5 sine 56 degrees, and I get the normal force from the wall is 80.9 newtons. Okay? Now, if we're like, okay, well, I needed to find this force, so we also can use the fact that F net equals ma. F net equals 0, right? And that has an x and a y component because there's horizontal forces. We'll say right is the positive direction, upwards the positive direction. So just like our unit 2 forces do the exact same thing. In the x direction, the net force, any rightward forces are positive. Any leftward forces are negative. Those are the only two forces. The frictional force and the normal force are the only left and right horizontal forces. That equals 0. So the frictional force actually equals the normal force from the wall. So the frictional force also equals 80.9 newtons here. Okay, part B. How far along the ladder can, let's see. So notice that we never use the coefficient of static friction here. Right? Coefficient of static friction. Why do we not need that? Because the frictional force, static friction, the coefficient of static friction is only used to calculate the maximum static frictional force. It is not used to calculate the static friction. Static friction is reactive. It can be anywhere from 0 to the maximum static frictional value. However, if we put a 75 kilogram person and we want to put him right before he starts to slip, at this point right before it slips, now we know the frictional force is going to equal the maximum static friction, which is mu times the normal force, and specifically the normal force from the ground. Okay, because that's where the friction is going to exert. So there's a couple things that are going to happen in our equations, our analysis for part B, is that we're now going to add another force from someone's weight of 75 kilograms, 75 G is his weight, somewhere at some location R up the ladder, right? So that's going to factor into the torque. So our torque equation is going to get modified a little bit, because you're still going to have this, minus 3 cosine 56 degrees times 200. But now I've added in a new force. And this R I don't know. This is what I would like to know. R is, it's also negative torque, just like this one's going to be minus R cosine 56 degrees. Just like the same way we've got 3 cosine 56 degrees there, the component perpendicular to the gravity, times 75G, plus the normal force from the wall, times 5 sine 56 degrees. That equals 0. Okay, so that's our net torque equation. The R is unknown. And we don't know this guy either. However, now we know the frictional force equals mu times the normal force from the gravity. Well, let's take a look at that. So we could plug that into there if we knew what the normal force from the ground was, right? And so this is where we're going to look at the Y forces, the up and downward forces here. Careful, we'll say up is positive. So all the upward forces are the normal force from the ground, minus, I have 200, and then the 75G. And those are both downward. So the normal force from the ground is 200 plus 75G. For the interest of making the numbers easier, I'm going to use G of 10. So it's going to be 200 plus 75 times 10, and that's going to make that 950 newtons. Okay, and then that goes into here, because that will give us the frictional force, which is 0.5 as the coefficient of friction, times 950. And that's 475. And then we can plug that into here, because the frictional force also equals the normal force from the wall. So then you can solve for R. So we put that all together. So you're going to get minus 3. Let's just kind of minus 3 cosine 56 degrees times 200. Then plus 475 times 5 sine of 56 degrees. Okay, so just combining these two terms, I'm going to get minus R cosine 56 degrees times 75 times 10. And then plus 1633 equals 0. And then you can solve for the R. 1633 divided by 750 divided by cosine 56. Get the R is about 3.89 meters.